Good evening. My name is Claire with my colleague Emma, and our project is all about it's a multi-strategy sparse learning for signal translation to voice. Our introduction, multi-strategy sparse learning for signal to voice is intended to address the issue of communication for non-verbal individuals for one reason or the other. Okay, our project is all about caring about the impaired people. Like we got voices from those people who can speak very well, and voices from people who speak while stammering, and we compared them and got the signals from them and translated them into fine voices, enabling the impaired people to communicate very well. The goal here is to develop a non-invasive real-time system that translates those signals to the voices. The non-invasive system is where there is no entering into someone's body. Okay, the better way to understand it. No anything that is inserted into someone's body in order to do what? In order for a system to be successful. And slide 3, we have the problem statement. And we have the current assistive technologies and their limitations. I've already talked about the problem statement. So here we have the typing-based communication. Requires a fine motor control. Here, they're showing you that typing requires someone to use their hands, but there are some people who are paralyzed who can do that. And the eye tracking system also, there is someone who is in coma, so that someone in coma can want to communicate if they can't blink. Even the gesture-based communication is the same. And we have the objectives, what we are going to do in order for our system to be a success. Here we're going to develop a real-time non-invasive system that translates EEG signals into text and speech, allowing individuals with speech impairments to communicate effectively. I talked about the non-invasive system. Yeah, that is understandable. Then develop a deep learning model that maps the EEG signals to text or phrases. Here, the deep learning model mimics how the human brain processes information. Then we are going to create a real-time system that converts EEG signals to speech. Yes, evaluate the system performance based on the accuracy, speed, and the user experience. Then enable individuals with disabilities to communicate using their brain signals, the way I talked about it, that we're gonna extract signals. And the methodologies we're gonna use. Here we have developing a brain to text system requires multiple signal processing and machine learning. And the steps we have data acquisition, like the way I talked about it, we got the signals from the voices, we got from the health and the sick children, those who stammer and those who don't stammer. And the audio processing, we are going to select the sound from those voices, the signals from those voices, and the feature extraction, extracting the audio files and displaying the required patterns. And classification is collecting that feature you've extracted from the signals. We are going to classify them. Here we have the collecting the data using labels of healthy and SLI. Let me invite my colleague, Emma.
Okay. This is Claire and Emmanuel, some setting for learning models. So the project you're working on is a machine learning model that would be able to convert voice signals to assist the speech impaired people. So to accurately convert these signals to text and speech, we shall need a data set of EEG signals which we currently don't have, and we use the dataset that has voice signals for children who uh, who are who are okay with who have good speech, who are not sick, and those who are actually impaired and have difficulty in speaking. So what you're doing is we are converting these these audio voices into a clean data set that will be able to compare and tell the pattern in developing the speech. So the feature selection you're doing is principal component analysis, and the algorithms we used are the random forest and neural networks. Then the evaluation metrics. So the proposed solution, so we had to bridge the gap between brain activity and communication so that we aid effective communication. So we wanted a real-time system that is non-invasive, accurate, and user-friendly. So it could be maybe attached to a phone, but right now it cannot, it just aids speech. So our project follows a structured multi-strategy sparse learning pipeline incorporating signal processing, feature engineering, and deep learning models to achieve high translation accuracy. Then the expected impact. So for individuals with disabilities, it enables real-time brain-to-speech communication. It improves independence and social interaction. So the person who has brain issues can be able to articulate their thoughts effectively to those he's trying to talk to. Then for medical and rehabilitation applications, it assists stroke and patients that have issues with speech in regaining communication. And it also helps in cognitive and behavioral interventions. Then challenges and future work. So the challenges we had were we had to look for a data set that had brain signals, EEG signals, which were currently not available. And then we had to improve the accuracy of brain to text models. So we have to evaluate the models, we shall create more multiple models, though right now we only have the ECG report. And then we try to improve the accuracy. Then reducing signal noise and real-time processing. So we had to look at the voice text so that we analyze them and get the best out of them so that they can be able to be used and in the model and the code to run perfect. In the future research, we're going to integrate EEG and EMG signals for better accuracy, expand vocabulary recognition for expressive communication. So that the model should be able to identify whether it's English or any other language and convert it to the required text or output. Then the conclusion. So the EEG-based speech translation offers a non-invasive solution to individuals. So it's going to work on individuals with speech impairment. It's going to enable brain-to-text conversion. Then the future advancements can improve real-time processing. So where someone could maybe have their phone and they send a message to someone without necessarily typing in the phone. So it could work with that real-time processing. Then potential impact, it transforms assistive communication for millions worldwide. So it would be useful in that communication won't be an issue now, it will be a solved issue. So that is it. I thank you for watching.